In metal 3D printing, specifically laser powder bed fusion, very thin layers of metal powder are spread inside a controlled chamber. A high-powered laser then scans across each layer, melting and fusing the powder to form solid metal. This builds up the final component, layer by layer. Traditionally, finding the right printing conditions like laser power, speed, or spacing relies heavily on trial and error. An alternative is advanced modeling and simulation, a smarter way to explore process parameters virtually. Hence, researchers at A*STAR Institute of High Performance Computing developed the Additive Manufacturing Digital Twin, in short, AMDT. This software platform allows users to run virtual simulations of the 3D printing process to predict optimal printing conditions, saving time, cost, and materials. It supports a wide variety of engineering alloys, including nickel-based, steels, titanium-based, copper, and aluminum. The current supported printers include the EOS M290 machine, the Akiniti 3D Mini, the Arcam A2XX, and user-defined printers. We begin by demonstrating the AMDT platform's capabilities using an impeller as our example component. First, we load the STL files for both the impeller and its support structures. Next, we define the element size and proceed to mesh the entire setup. From here, we calculate the thermal history of the entire component using the finite element method. This step identifies areas of potential under or overheating, factors that can lead to defects and affect the material's microstructure and mechanical properties. Once the simulation is completed, users can simply click on any point in the mesh to inspect its local thermal history, enabling detailed, site-specific analysis. Using our proprietary algorithm, the mesh is segmented into regions with similar or distinct thermal profiles. This is crucial for understanding how temperature variations influence the material's microstructure. Diving into the details of the powder, the internal discrete element method simulation calculates the powder's packing density based on user-defined powder size and shape distributions. This capability is seamlessly integrated with the ray tracing model to provide a clear view of the powder's absorptivity, offering insights into how each specific powder batch interacts with the energy source. The next step is to apply the AMDT workflow into our model. That is built on the phase field method and integrated with the lattice-Boltzmann method. This is to simulate fluid flow and solidification within the melt pool. The approach has been rigorously validated for predicting melt pool dimensions, defect formation, and grain size distributions across a wide range of materials and process conditions. Using our classification algorithm, we run dedicated simulations for each key region of the part, applying temperature boundary conditions tailored to their specific thermal environments. Once local cooling rates are computed, the rapid solidification model simulates the segregation of solute elements, like niobium in Inconel alloys. This allows users to assess if the process conditions may lead to the formation of brittle phases, such as the Laves phase. At this stage, the AMDT workflow advances to calculating mechanical properties, using our proprietary mean field crystal plasticity model. This model draws directly from the microstructure and defect data generated in the previous steps. It demonstrates our tightly integrated approach, enabling in-depth analysis of process structure-property relationships. With multiple microstructures representing different locations in the part, the model is able to generate multiple mechanical properties. When heat treatment is required, AMDT offers two powerful models to simulate precipitate nucleation and growth. One uses an explicit 3D approach to visualize how precipitates form and evolve over time. The other takes an implicit route, calculating precipitate behavior analytically for faster insights. In the final step of our workflow, we move back to part-scale simulations to calculate residual stress and distortion. The mechanical properties previously computed at each key location are now mapped back onto the full mesh. With these values in place, a thermomechanical simulation is run. Users do not need to make assumptions, as AMDT derives the properties internally. To enhance usability, the same algorithm and color scale used in GOM scanning were re-implemented. allowing users to compare the real 3D scan of the printed part with the digital simulation results. With AMDT, manufacturers can fully unlock the potential of additive manufacturing, minimizing costly trial and error and enabling first-time right printing.